All right, ladies and gentlemen. Chapter 5, sections 3, 4, and 5. Questions. Fundamental theorem of calculus, net change and indefinite integrals, and substitutions. This could be a very short day. Mhm. Let me add to you this thing. This is today. This is the last day of class. On this calendar, that's the final exam period. Two weeks. Yes.
Can you go over 16 and 5.3?
5.316. Yes. 5.3. Let's do something similar. How about 17? 17 is the integral from 1 to something slightly different, and we want the derivative of this, right? Okay, let me copy the problem down. Okay, we're asked for dy dx. When I'm taking the derivative of an integral, the fundamental theorem of calculus says that when I take the derivative of an integral that goes from a to x, all I have to do is replace the variable in the integrand with an x, right? So the derivative of the integral from a to x of f of t dt is f of x. I want the derivative of this thing. This is what the fundamental theorem of calculus part 1 says. So really, I could rewrite this request as the derivative with respect to x of the integral from 1 to 3x plus 2. Copy all this stuff down. This is the sneaky part. My upper limit is not just x. That's the problem that doesn't make me use this automatically. That's stuff, right? Rattle, 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 rattle. I hear the chain rule in the back of my head. Take the derivative in x, but it's not x, it's stuff. What happens when I take a derivative of stuff? What's the chain rule tell me to do? So I'm going to think of this as the outside and this as the inside. So the derivative of this thing, as if I was leaving the stuff alone, would be f of stuff. And that's my benefit right there, is that I don't actually need to do anything other than copy the stuff into here. And now I hear the chain rule, but wait, there's more. And I multiply by the derivative of the inside. Well, what's the derivative of the inside in this case? And I'm done. Presto. Now, in the problem you actually asked me about, the same thing occurs. I have the integral from 1 to stuff. Only the stuff is a little more complicated, so its derivative will be a little more complicated. Oop, wrong button. That button. More questions. There are a lot of functions that get defined as integrals whose actual numerical calculations are easy, but whose antiderivatives suck. So there are a lot of places where we do this and simply go, if I need the derivative, I'll use the fundamental theorem of calculus on the integral. And having an integral defined function shows up a lot. We'll see it a lot in probability statistics. Talk about distribution functions and hypothesis testing. More questions. This is one of my favorites for integral defined functions. Actually, e to the negative x squared. I shouldn't do this alone. There's a number that goes out in front of this, but it's not exactly relevant. If you graph f of x equals e to the minus x squared, you'll get a very familiar looking picture. That's the curve most people call a bell curve. And when I put that 1 over square root of 2 pi out in front of it, that's the standard normal distribution in probability. One of the things we want a lot is the area under this curve. But I don't know how to do this at all. None of the tricks we have learned so far help me find the antiderivative for this. It turns out that our fundamental theorem of calculus has a major drawback. And that is, I can only find so many antiderivatives. And there are a lot of functions whose antiderivatives simply cannot be written in terms of the functions we already know. And when we find such a function like this one, we're going to say that this antiderivative has no closed form. That means we can't write it in any of the functions we like to work with. Exponents, logarithms, trigs, inverse trigs, even functions we don't see very often, functions like the hyperbolic function or other sorts of crazy functions, there's just no nice way to do this. The result means that the only way to get there from here is to approximate. If I want areas under this curve, I'm going to use a Riemann sum. Oh, man. Most of the time, because this graph is symmetric from left to right, I can use the symmetry principle we talked about, and I can really only go from 0 to the right. So frequently, we'll be asked for some value, what is the integral from 0 to a? And rather than find this by an antiderivative, I have to do a Riemann sum. Advantage. It is really, really easy to write a computer program to do this with, I don't know, 100,000 rectangles and have it be done in a second. So we cheat. And quite frequently, we simply do that and work all these values out in advance. And in my statistics textbook, I have exactly that. It even looks like an integral. The area under the curve I want from 0 to whatever, in this case they're using z instead of a, and they'll give me 2 decimals, so 0.41, the area is 0.1591. And I can keep going as far to the right as you want. You want areas to the left? Then your z value would be negative, but the area, you just flip it over to the right side, from the left side to the right side, you get the same value. The majority of probability theory. Basis around figuring out, can I use these tables? And if so, which one should I use? Because there's more than one. This is just the most common. Ask me more questions before I wander off again.
We're gonna do this again next Monday. Because Wednesday, Thursday, Friday, I'm teaching 3 new things, and Monday is question and answer. You all don't need to be sitting here staring at the ceiling. I don't have any reason to keep your butts nailed to these chairs. I will see you all on Wednesday. Have a wonderful rest of your day.